To help us with that, we have Peter Lee, President of Microsoft Research. Peter leads teams that incubate AI-powered products and business models, any one of which may be tomorrow's next big thing. Before joining Microsoft in 2010, Peter was a research scientist at DARPA, and before that, professor at Carnegie Mellon. He has a special interest in how AI can be applied to medicine. And last year, Peter was named by Time magazine as one of the 100 most influential people in health and life sciences. Peter, welcome to EmTech. Well, thank you. I think you've got a presentation to start us off?
Sure, a short one. Thanks for having me here. It's really a thrill, and I am a little bit nervous because I think what I was asked to talk about is what's next in the next 1 to 3 years in AI. And I honestly, the more I've fallen into the AI rabbit hole, the more I feel I don't even know what's coming in the next 1 to 3 days. And so it's a little bit intimidating. And part of the reason I think that it's intimidating is we're in a state, and the way I try to explain this to my wife is to imagine that you're in an alternate universe where electricity hasn't yet been delivered to people's homes. People in their homes are using candles or fires to light themselves, light their environments. And now someone invents copper wire and discovers that it transmits electric current incredibly efficiently from point A to point B. And we just know in our guts that this is going to transform life for the better for everyone. But we don't yet know why, because no one has invented the light bulb. And now we have gigantic, huge, multi-trillion-dollar companies transforming themselves into copper wire companies, stringing copper wire down every street into every home around the globe, confident that those light bulbs are going to get invented. And not only light bulbs, but someone will figure out that you can wind these things around pieces of metal and make electric motors, and maybe even someday transmit digital signals on these things. And that is basically in a nutshell, the situation that we're in today. And that's not to say that Microsoft isn't making a lot of money on AI. We are. But the true value of AI, I think we haven't yet imagined, and it hasn't yet been invented. And yet we are in a race to have the deployment infrastructure to deliver AI to the entire world. So now, what can I possibly say about what's next? And there is one area that, at least for me, has captured my imagination and has caused me, in my leading role at Microsoft Research, to devote a considerable amount of resource into investigating. And it is a hot topic at MIT and at universities and at great companies around the world, which you could just refer to as AI for science. And that is the idea that the AI technologies, the architectures around transformers, diffusion models, and so on, might work just as well, if not better, for learning the languages of nature than they do in learning our language, the languages of human beings. As just one simple example, this is a picture of a protein that is associated with the disease tuberculosis. And if you look very carefully, there's a little bit of a colored molecule that has been designed entirely by a system called TamGen, which is built using 3 generative AI models, 1 diffusion model and 2 transformer models, that has designed on its own that potential drug molecule candidate that binds over 40 times more effectively in a key target in that tuberculosis protein. Incidentally, everything I'm going to talk about today, I am going to talk about and try to ground it in the real world of 1 to 3 years. And so TamGen is available to anyone. It's open source, and my colleague Asha Sharma delivers these things on the Azure Foundry. But if you don't want to use something from Microsoft, there are dozens of laboratories around the world that are chasing after the same sorts of capabilities, and we even have Nobel Prizes by some great scientists at Google and University of Washington and others. What is going on with these things? Well, with generative AI, we dream of being able to write down in a prompt or some specification of what we want a molecule or material that we are designing to be, and then generative AI should magically give us that thing. And that is actually the backwards order of the way science has always been done computationally. Computational science traditionally has gone the other way, where we take a simulator, typically written in Fortran, and we run that simulator to witness computationally what the properties are of some proposed molecule, some proposed physical system. And if it's not right, then we change the parameters and rerun our Fortran codes. Those Fortran codes have been exceptionally important. They've driven a huge amount of computational science over the decades, but of course, they are incredibly slow. And so, for example, on that tuberculosis drug candidate molecule, it would have taken several million years of computation time using those Fortran codes to come up with the same type of molecule. What is very interesting, though, is that these simulators are based on the precise physics of these molecules. And so these simulators actually generate perfectly labeled synthetic training data that allows us now, with our new generative AI architectures, to train what at least we in Microsoft have been calling emulators. They emulate these classical simulations, but because they're using AI, they are able to do so typically at an acceleration of 1,000 to 10 million fold. And in fact, for that TAMGen, there was over a 10 million fold speed up in the design of that molecule. And incidentally, this is one reason why we at Microsoft, but we're far from alone. There are great labs around the world pursuing this. This is another reason why we are so interested in quantum computation, and we're so heavily invested there. Because the first and foremost quantum program that we've written, that we are dying to be able to run, is a molecular simulator. And to be able to generate, again, training data much, much more rapidly and much more cheaply than we're doing today to train these AI emulators. And so there are some early tantalizing examples. And again, every example I'm going to talk about here, you can have. It's open source. It's on the Azure AI Foundry, or it's on Hugging Face, whatever you want. And again, if you don't want to take it from our labs, there are just amazing things going on here in the Boston academic and research ecosystem, and as well as great companies around the world. But biomolecular dynamics, showing the conformations of molecules, again, with absolute chemical quantum precision. Materials design, getting the precise sort of material and electrical properties in design, and magnetic properties in design materials. That's in a model called MatterGen. We've run millions of hours, costing us quite a few $1 million, millions of hours of global climate simulations, atmospheric simulations, with the resolution turned way up, down to 0.1 degree of resolution, in order to generate training data to train a model called Aurora that then shows tremendous foundational capabilities. And what I mean by that is it's trained on those climate simulations, but then we take a small amount of data from the Copernicus atmospheric modeling monitoring system that pertains specifically to nitrogen dioxide dispersion through the atmosphere. And we find that that fine-tuning of that foundation model gives us the most precise pollution dispersion models ever developed. And again, trained purely on that synthetic but very physically precise training data. And then we even have our world action model, just learning, observing people playing video games, and then from this simulated data, getting emulators able to learn the world model. Where we're going with all of this is to really drive at the heart of quantum physics. And if you go back to Schrödinger's equation, there was a Nobel Prize some time ago that really defined something called density functional theory, or DFT, and there's a specific functional, and there's a whole zoo of machine learning and other approximation algorithms that are used to calculate various aspects of that DFT functional. What we're finding is precise simulation of these things at scale gives us training data that gives us a much more general and much faster emulator for DFT. And that is something that has commercial impact, we believe, because about 60% of HPC workloads today around the world involve DFT solutions. And so just to close, I think what I would try to claim here is that in the same way that we found that generative AI architectures are shockingly good at learning from the digital exhaust of human thought and expression, we're finding that the same is likely to be true for learning the languages of nature. Thank you.
Thank you. Please take a seat.
Yeah, thanks.
That was great. It's nice to see.
I was nervous because what do you say? You asked me to talk, 1 to 3 years from now.
Yeah, I wouldn't answer that question. I'm surprised you even came. But I'm glad you did. Yeah, I was going to say at the end of 3 days of talks and lots of conversations, I'm going to do the foolish thing of trying to get you to help us tie a few things together. It won't be a pretty bow, but we'll do our best. But already I'm seeing connections with you talking about these simulations and this universal language of nature. It makes me think of we had Scott Penberthy from Google yesterday, who was calling today's AI universal approximators. It allows us to simulate anything we want, and that's a very, very powerful idea. I also loved the copper wire analogy. I mean, of course, you're not the first person to compare this to the invention of electricity, but that focus on the copper wire and all the big companies want supplying copper wire, I think is fascinating because nobody, back 100+ years would have sort of set up a business putting copper wire in all our streets before we had the light bulb. So why are we doing that now? Why is everybody so convinced that putting the copper wire out is worth doing when we don't yet have the light bulb?
Right. By the way, the copper wire thing is also, I think, interesting because, what are regulators to make of this?
Yeah.
Because people are getting shocked all the time. Maybe some houses are burning down. There might be some crazy people putting their tongues on this thing.
Yeah. And other people are saying, "Wait, it's just a wire. It's just a wire."
Yeah. Or other people, calling themselves copper wire companies, but what they're doing is selling clothes hangers made out of wire. So So first off, I think that there are monetization opportunities at scale already. These technologies are improving a lot of things. They're improving search. They're improving ad targeting. Our enterprise copilots are selling extremely well. Actually, the fastest growing copilot product at Microsoft is an AI scribe for writing clinical notes. Mm-hmm. So things are happening. But I think what I'm really trying to say is that 10 years from now, we'll look at all these things as sort of trivial and foolish. And maybe a way to...
Which things exactly?
The things that we're trying to do with AI today.
Right.
They're limited by the limits of our imagination. So a way I try to explain this, and this relates to quantum, is the field effect transistor was invented by Lilienfeld in Germany in 1926. And then it took a couple of decades for folks at Bell Labs to actually make one that worked. But here's what people don't remember. Then from 1945 or from 1946, it took until 1951 before the first commercial application of the transistor happened, and that was the tone generator to make beeps and burps to switch telephones. And then another 4 years before the second commercial application, which was the AM transistor radio. Notice there's no digital computer in there. And if you go all the way back to 1926, Lilienfeld could not conceive of a digital computer. So I think the things we're thinking about in AI today are the moral equivalent of tone generators and AM transistor radios. What will be the real things that will just transform our lives that we can't live without? all day, every day. I think we're yet to see those things.
Right.
Having said that, at least speaking for Microsoft, we're doing very well, and our shareholders are rewarding us for selling a lot of AM transistor radios. So it's a good business.
It's a good business. Yeah, nobody quote you on calling those trivial things.
Right.
So, I mean, another way of talking about this, and there's so much buzz, so much noise. How do you go about finding the signal? I mean, and also I'm leaping between metaphors here, but when we spoke a few weeks ago, you had this other nice image of AI as like a blanket that's just been dropped from the sky, and it's settling now, right, into the sort of nooks and crevices. But once it's settled, there will be some obvious peaks, spikes where the applications are really breakthroughs. I mean, is there any way we can sort of predict where those are going to be?
I think I said the same thing when we talked before. When you get the answer to that question, please tell me. Because in a way, I think my most fundamental and important accountability to Microsoft is to answer that question. And I honestly have no idea. There are fundamental values about the value of research that, in my mind and my heart, give us the best chance to do that, to maintain a culture of independence, to have an understanding of the need for balance between kind of bottom-up independent ideation and top-down mission-focused drive, and so on and on. But these are all, at the end of the day, just my personal biases. If I reflect, I think I've gotten a lot of things right in my career, but I've missed a lot of incredible things also, or just even dismissed them. Yeah. There was a lot of talk about deep learning, and when I joined Microsoft in 2010, I was going through all of the existing projects that were funded in Microsoft Research, and there was this one project that was instigated by Jeff Hinton and his students who were spending the summer. It was actually the previous summer, 2009. And they had proposed, hey, you guys, you do speech recognition. Why don't you use this layered cake of neural nets to do speech recognition? And by the time I arrived at Microsoft Research strangely had agreed to fund that project. I'm certain if I had joined Microsoft Research a year earlier, I never in a million years would have okayed that, because I knew enough about speech recognition to realize that was completely ridiculous. And of course, the results were shocking. Andrew Ng was hanging out at Microsoft Research, and so the next year he went and hung out with Jeff Dean and asked the question, would this work for computer vision? And of course, we're detecting kitten videos all of a sudden. And so, there have been so many times when I've just been wrong, but I think ultimately, you just need to be able to admit, both as a person and as an organization, that you've missed some things, not be ashamed of that, and jump on it.
Yeah, I mean, thinking about that trajectory you were just outlining, we started the show a couple of days ago with discussion about sort of exponential growth and the advances, and some people are happy to sort of project that exponential growth and make predictions about where we're going. And we've happily avoided the term AGI as much as possible in the last few days. I personally dislike it. I know it splits the industry. We also had Ali Farhadi from the Allen Institute on stage yesterday, and he told me not so long ago, joking, I assume, but if any of his PhD students use that term, instant fail. And yet, on the other hand, there are the leaders of some of the biggest labs in the world, with a very straight face say, we are making AGI. And to pick two names at random, Sam Altman is on one hand making AGI happen, and Satya Nadella thinks it's a nonsense distraction. I mean, how should we make sense of this wild disparity?
Yeah, I think I side with Satya. By the way, on the day that GPT-4 got revealed to the world at Microsoft Research, we published a paper entitled Sparks of Artificial Intelligence. And Satya never misses a chance to criticize me. for that. And I think he's got the right point. And the way like, what the heck is AGI?
Yep.
So here's the way I think about it, if I can just be an academic research geek for a minute.
Please.
In my career, I count. Let me ask this question: who here is not carrying a mobile phone with them right now? I don't see any hands raised, which is a good thing, because if there were some unlucky person who maybe forgot it in their hotel room or at home, you'd be feeling pretty bad right now. Naked, vulnerable, all of that stuff. And so in that mobile phone, throughout my research career, have been 6 triumphs of academic computer science research that you literally can't bear to live without at any moment of the day. There is VLSI design emerging out of academia in the late 70s. There is software-defined mobile wireless network radio. We can just go through these 6 triumphs. There's GPU ray tracing and 3D computer graphics. And each one of these things, academia sacrificed itself to make these things possible. They became incredibly hot topics in research, funded by our government. And then when they transitioned to industry to become the infrastructure of life, virtually all research in those areas in academia stopped. It matured. So my thought here is, what counts for me is, will generative AI become the 7th in my career for that to happen? Will generative AI power things that you cannot bear to be without for any moment of the day, that you would literally feel incomplete and unsafe? And if you could call that AGI, but I don't think it's quite the same idea. And I would say the bet that at least Satya Nadella has put Microsoft into making is that he's betting that it will happen, and it will happen soon.
Yeah. Which is a much more concrete way of thinking about it. We have a few minutes left, but I'd love to go to questions in the room if there are some. Could we get the lights? I can see some hands, but who has the mic first?
Okay.
At the back.
Thank you. Very nice, and I'll build on your academic point. I'm a professor at a university, and the question is, have you been dealing with universities in terms of rolling out AI, and more generally, how would AI help reimagine or reinvent academia?
Yeah, so I would say, so we have been doing that. We have several programs. I can't say I'm particularly impressed with the outcomes of what we've done so far, and that's probably our fault, not academia's fault. We worked with several, almost 2 years ago, we worked with several universities to have private tenants with access to APIs and models. And some universities, like one that I would point out is the University of Michigan, put in quite a bit of work to integrate things into student information systems and so on. But it hasn't been the transformation that now 2 years later I was maybe hoping and expecting to see. I think things will happen, but things along those lines I think are important. One of the things I would like to see us do and industry do is to provide more access to compute infrastructure for open model development. I think that could make a big difference. But it has, frankly, just gone a little bit slower than I would have hoped.
Go ahead.
Hi, Kareem.
Yeah.
Kareem Azaram at Novartis. So I wanted to come back to your premise about, how will AI give us insights into the natural world and specifically perhaps life sciences?
Yeah.
But today we heard about Schrodinger equation. Yesterday we heard about Navier-Stokes. And as a mathematician, I spent a good amount of time studying these. They give us significant insight into life, and we also it took us quite a bit of time to develop the tools to be able to understand the systems that we're studying. Do you see these, AI models as sort of more pattern recognizers, in other words, giving us information that's out there we haven't noticed? or they're actually going to help us discover new aspects of our worlds. You know, for example, can they lead us to a unified theory, for example?
Yeah.
Like another Schrodinger, another Navier-Stokes. So where do you see this going?
Yeah, a really great question. We probably don't have enough time to get into that. Maybe a couple of quick things. First off, I think that these things will enable sort of ab initio design of physical systems from the ground up. Whether that will have true practical value, like will we ever ab initio from the Schrodinger's equation on up be able to design a drug that you would put in a human being? I have no idea. Commercially, today, the way the pharmaceutical industry works, you know, those phase 1 designs are a dime a dozen. So commercially, it seems problematic. So I would expect commercial drivers are going to not be based on ab initio designs, but instead be used to arbitrage of the multitude of people doing molecule design, which are the ones I should bet on. And so that's kind of a higher level kind of thing. So there's going to be a push and pull there. But on your more fundamental question, I would expect within 5 years we will start to see some physics, chemistry, and biology discoveries that will be discovered autonomously, written up autonomously, submitted to major leading journals. And I think the editors-in-chief of those journals will have a time trying to figure out what to do with those.
I'm going to get myself in trouble and carry on taking questions, even though we're out of time, because these are great questions. So 1 and 2, if they're quick, please.
Dick Oddie from Promex, Santa Clara. How close are we to having machine consciousness and to having a personality live in what I'll call the cloud?
Yeah, that's another one where I always say, when you figure that out, please tell me.
Yeah. There's also supposed to be a quick question, but
Yeah. You know, I think that one of the things we're finding in the healthcare space, there was a beautiful study, controlled clinical study done jointly by UC San Diego and Stanford on looking at email responses to patients, you know, in the medical setting. And, you know, it measured in a randomized study that the AI was just as accurate as human clinicians, but by a factor of 9 to 1, the machine-generated responses were deemed more empathetic, more kind, more personable, whatever you want to say. And so there's something strange, you know, going on there. You know, I think human beings are so frazzled today, and so I wouldn't call it consciousness, but the observation in that control study, there was a line in the report that said that human beings, the human doctors, on seeing the draft written by the AI, were often observed pausing for 15 seconds, apparently reflecting on the life of that patient. So there's something about the relationship between man, machine, and other human beings that I think potentially could be made better by forcing us to remember and reflect on each other's lives in a different way. I hope that makes sense.
Yeah. Well, was there one more question there? Oh, sorry. Just because I did say. Go ahead.
Rupeng An from New York University. So you mentioned about the machine is able to now speak or interpret the language of nature, and you showcased one of the examples of an emulator. But that is because we know the underlying physics.
Yes.
We know how fundamentally data is generated.
Yeah.
As a social scientist, we study a lot of social behavior, and we see this a lot more difficult to interpret and to make sense of. Though in this large uncertainty associated with human behavior, the policy, the society, how would you see that AI will be able to help? Thank you.
Yeah, it's really an interesting question. And even with something like biology, the amount of diversity that is possible. I mean, there have only been, 106 billion human beings that have ever existed. So even if we had DNA samples from every single one, in today's world of generative AI, we might not have enough data to train a model, for certain types of problems. So I think that the fundamental question, and we saw this in the Aurora weather model, that foundation model, what shocked me was it was not trained at all on any nitrogen dioxide dispersion data, literally zero. And yet, with a very small amount of fine-tuning on collected nitrogen dioxide data, it was able to surpass all of the specialized pollution dispersion models out there. So I think it's really unclear how this will play out, but it's not inconceivable to me that even in, say, trying to understand social systems, that we may be able to build very capable foundation models on large amounts of simulated data. I don't know, ultimately, but it seems possible. We can't discount that possibility.
Thank you. Yeah. Thank you. There's nothing more reassuring to me to have you come on and say you don't know, because it just makes me feel a lot better.
All right, thanks.
Thank you so much.